Okay, today we're talking about quantitative chemistry. Now this is all about calculations, making things balance, accounting for all the constituents of an equation to quantify where things have gone. And there's many equations we're going to do, but today we're going to talk about conservation of mass. That's 4.311. Unbalanced equations will be the next video. So let's get straight into it. So imagine, here's a picture of me. As you can see, I've spent a bit of time in the gym. If I decide, first of all, my mass is 160 kg, I feel a bit hungry, I decide to, feed my muscles with my favorite nutrition, which is a bar of chocolate. And if this weighs 300 grams, okay, so as you can see there, 300 grams. Remember, 1,000 grams equals 1 kilogram, right? So if I eat this chocolate and then hit the scales, you will see that my mass, or my weight as we say, is 160.3 kilograms, as we can see here. That means whatever I've consumed, because I've ate the whole bar, is then quantified as my total mass. So no mass has escaped, no mass has not been accounted for. If I've had 300 grams, that means that's added on to my original mass. So going back to the conservation of mass, the easiest way I like to explain this before we talk about chemical reactions is, wherever you add to a reaction, it has to be accounted for. So now let's look at an example. So here we have methane over here, okay, we're adding 2 oxygen molecules, okay, it produces carbon dioxide and 2 water molecules, okay. Now if you look at all the constituents, on the left hand side we have reactants, I'm going to label that R, and products on the right hand side. If you look at all the reactants and the products, even though they've been rearranged because the chemical reaction has occurred, in this case it's a combustion reaction, all the elements are still there but in different forms. So mass has just changed form, it hasn't just disappeared, we haven't just created a particular element. If you look, there's 1 carbon in the products, which is here, and there's 1 carbon here, so that's the same on both sides. That makes sense. If you look at the hydrogen atoms, there's 4 here, 1 2 3 4, and there's 1 2 3 4 here, which leaves behind oxygen. So we have 4 oxygen atoms here, 1 2 3 4. On the product side, 1 2 3 4. Now this is the principle of the conservation of mass. What I'm saying here is every element is accounted for on the product side, so we can't just randomly create things, okay. Whatever's on the reactant side has to still appear in the product side, even though it may be in a different form because of a new compound being formed, some kind of chemical reaction. And the simple way I explained it was a picture of me eating 300 grams of chocolate. My original mass was 160. If I eat the chocolate, it's gone. The chemical reactions occurred into my body, all the digestion process is happening, but until I release any of that food or use it in the respiration process, I am now 160.3 kilograms. Okay, there's the theory. Now let's put it into some kind of practice. Let's practice what we're preaching here. Now there's an exam question from the AQA exam board. So have a quick read. A student investigates the law of conservation of mass, right? Then it states the law. Here's the method. We're pouring lead nitrate solution into a beaker. It's labeled A. Pour potassium chromate solution into a beaker B. Measure the mass of both beakers and contents. Pour the solutions from beaker B into beaker A. Measure the mass of both beakers and contents again. Okay, so that explains what we're doing in this procedure. When lead nitrate solution and potassium chromate solution are mixed, the reaction below takes place. So there you have your lead nitrate reactant. Okay, I'll draw a line there. There's your other reactant, which is potassium chromate, and here are our products: lead chromate and potassium nitrate. You see, again, chemical reactions occurred and there's been a rearrangement, but all should be equal on both sides, and we can check that in a second. But let's look at the question. What would the students see when the reaction takes place? This is not conservation of mass as such, but it's something we would learn later on anyway. If you notice, it's an aqueous solution, aqueous, and we have a solid formed. The lead chromate becomes solid, so we would say a precipitate is formed, and that would get you the 1 mark. Okay, now here's the conservation of mass. Now it says show that the law of conservation of mass is true, so we need to confirm that, verify that it is true. And the law states that mass cannot just be created or destroyed, it's just transferred from one point to another in a chemical reaction. So let's prove that. Use the data from the table above. So beaker A and contents before mixing, beaker B and contents before mixing. Okay, so A is the lead nitrate, so let me just label that there, and B is the potassium chromate, so that's the reactants. Okay, so the reactants are both here and here. If we add them to masses up, we would get 2, 5, 6, or actually it's 7, I'll look at my calculator, 0.68 grams. Okay, 257. Now if we look at the contents after mixing in beaker A, right, and contents after mixing in beaker B, so that would be the products. Okay, so if I have 154, well, I'll label that 3 and 4. If I add these two up, so 154 plus 103.58, the mass is still 257.68. Okay, so that's the mass, the total mass here. Now where would we get these masses from? We would use the periodic table. Okay, this is a balanced equation. I'll talk about how we balance these things later, but for now this has proved that the conservation of mass is true, the law that is, because the reactants weighed 257.68, that's these here, and the products also have weighed 257.68, so that verifies the law. I hope that makes sense. That's enough for today. I'll see you in the next one.